Hello and welcome back to Calculus 1. It's this Saturday morning, right? Everyone is happy, can't wait for the weekend. So here it is. We're going to do some calculus, right? So 4.1 is on minimum and maximum of a function. We are constantly interested in what we call optimization. We want to know the maximum profit. We want to know the minimum cost. We want to know the maximum volume while minimizing the surface area. If you minimize the surface area of the box, that means that you are using the least amount of material to build the box. So that means that you are saving on cost. But maximizing the volume of the box means that you can ship a lot of stuff in that box, which again maximizes profit and at the same time minimizes cost. So, we are interested in that. We are interested in the maximum price of a stock. We are interested in the maximum energy. We are interested in the, minimum energy as well, right? So there's a lot of optimization that is to be done, and calculus is the one that computes that. So we start, we are going to do word problems on this topic in 4.4. Not sure if we're going to get there today. The first three sections are sections that are not applied. They are all procedures and concepts from calculus on how to optimize, how to relate graphs and derivatives, and also how to graph functions by hand. The idea is to learn how to graph, let's say, sine squared of ln x, all right? Now you might go ahead and say, but why? We have technology to graph that for us, and that's true. But in the process of learning how to graph by hand, you learn much more important skill for your later careers, and that is reading the graphs and understanding the graphs and being able to understand what they show. So we are going to, push all of this together. Entire chapter 4, since we are starting chapter 4 now, is on application of derivatives. So there will be more tangent lines, but there will be also approximations. There will be some limits as well coming back, some numerical methods for calculating things. And then another two sections of word problems, optimization and differential problems, are all in this chapter. Now, the last section of chapter 4 is antiderivatives, which is in introduction into integration. And please realize, I'm going to see you another 5 times. We have 5 classes left. That's it. So, why, disappointed? I know. That's... Yeah. So we have 5 classes left. We have 14 sections to go, I believe, which is not an issue, not a problem. 14 sections, 1 exam. We definitely have time. It's just, having exam today doesn't mean you're done, right? There's another exam coming in, let's say, 3 weeks, and then final exam in 6 or so. So, don't let the guard down. This was round 2. Now round 3 starts. That's that ping, the bell, right? Round 3. So let's talk about min and a max of a function. Here is the first concept that we need to understand. So we are going to have in our xy coordinate system function f of x. And we can see that that function has a point for a max and a point for a min. Now, these 2 points, this min and max, are both what we call local or relative min and max, because if you take a look at the elevation over here, which is somewhere there, you see that there are higher points than the max. So we are going to distinguish between local or relative min and max, and absolute. And I'll draw pictures, we'll understand what those mean. But before we get there, we all understand the concept of a minimum and a concept of a maximum because we're just alive and roaming around. So now, when you're looking at that maximum and when you're looking at the minimum, you see that they have a common feature. And that common feature is that the slope of the tangent line at that point is 0. So if I am to draw tangent lines, I would see that for both of these lines, slope is equal to 0. So this is what is going to help us to find locations. In this case, x1 and x2, to find locations at which these occur. So when I give you a function like, let's say, x squared, you all know that x squared has a minimum at 0, 0, right? So it has a minimum at x equals 0 and y 0 when you compute y. You probably know min and max for any basic function which you memorized, like absolute x, sines and cosines, right? They have infinitely many mins and maxes, right? So sine and cosines have infinitely many extreme points. So the goal of this section is to learn how to compute these locations, x1 and x2, where these points occur. Now, these points where we have min-max are called critical points. And we are going to define critical points, and we are going to then see which way we find critical points, and then later on find the ways of understanding which one is which and so on. Now, let me go back to the talk about absolute and relative min and a max. So I'm going to draw a function like this. We have this one over here, again, has a horizontal tangency, slope is 0. This is going to be the absolute max, because that is the highest point on the entire graph. This graph never bends up to have higher points than that absolute max like the previous one did, right? So that is the absolute max because it's absolutely the highest point on the graph. Now we also have this one over here, which also has the horizontal tangency, and this one is going to be relative max, also known as local max, right? So you can think about it as I don't know, president or the king or the emperor or whatever, right? As the absolute max, and then relative max is like a governor or a mayor or something, right? So it's the boss in his own backyard, right? So that's that stuff. And we also have in this picture this over here, which is relative min. And the reason why this is a relative min is because right here and right here there are points that are lower. They have a lower y values than that relative min. So that cannot be, right, relative min. Now I can draw this function upside down like this. And if I draw the function upside down, then we finally have the absolute max. So min, sorry. So this is absolute min. Absolute min. And this one over here would be, again, we have the horizontal tangency, relative min. And we also have a relative max over here. All right, relative to what? Well, to its own neighborhood. All right, so you have a neighborhood around each one of these points, and in this neighborhood, that's the maximum, right? But if you go far out, you see that all of these points above the line are higher values than this relative max, so we can't call this relative max absolute max because they're higher points. So that's what we have. I hope you understand the difference between local, relative, right, and absolute. So absolute, min, max. Sometimes they're also called global, depending on the book you are reading. So you have absolute and global, and then you have relative and local. How about to write that? So if you just, pick up some websites or YouTube videos or something, you know that these words mean the same thing. Good. So now let's go and write that min/max occur at critical points. So they occur at critical points. And it's our job to first define a critical point, because we can. I want to use the same wording as your textbook. So here it is, definition. So an interior point of C of the domain, anterior point C of the domain of f of x, at which f prime of C equals 0, or f prime of C does not exist, is called the critical point of f. So critical point of f of x. What does this mean? Yes. An interior point C of the domain of f of x at which f prime of C equals 0, or f prime of C does not exist. That's D and E. Does not exist. So, in other words, to find critical points, number 1, set f prime of x equal to 0, or number 2, f prime of x does not exist. Now, this does not exist is a little bit tricky situation, but it has to be there. So I'm going to give you example 1 and then example 2, and then we'll do obviously more involved examples. So the most basic examples we can think of is y equal x squared. You will take the derivative of this, so you have your y prime is equal to 2x. You will set that equal to 0. When you solve the equation, you get x equals 0. And you know this is good, because when you draw x squared function right here, you see that it has the minimum at x equals 0. Now you can go and plug x equals 0 into original equation to get the y value, right, to have x comma y. But we want to find now the location on x-axis where we have this critical point, which in this case turns out to be minimum. So that's the first part. And most of the problems are solved that way. Not all of them. The next example is y equals absolute value of x. Well, for the derivative of absolute value of x, you guys have the derivative everywhere except at 0. So, absolute value of x is not differentiable at x equals 0, which implies critical point at x equals 0 by the definition, by number 2 up there. So now, if you draw the graph for this, you know it looks like v, and here, again, x equals 0 is the critical point. It doesn't have to be at x equals 0. Right, we can shift this left, right, and so on. But I hope you understand that there are two ways to get critical points. Now, why f prime does not exist is dangerous. Because vertical asymptotes get preserved from a function into a derivative. Remember the derivative of 1 over x is negative 1 over x squared. So 1 over x is not differentiable at 0 because you have vertical asymptote there. And then that vertical asymptote is preserved in the derivative because negative 1 over x squared also has a vertical asymptote there. So you have to be very careful with the does not exist part. In some cases it produces a critical point, but in other cases, I would maybe say in most cases, it's going to be a vertical asymptote, and we know that we cannot have a point at the vertical asymptote. Vertical asymptote means the function is not intersected there with that x value. So that's the tricky part. Luckily for us, right? The vast majority of the time we are using this part. Sometimes we are using this part, but when we are using this part, most of the time it's not a critical point. Right? So it's kind of even hard to find examples that work that way. But again, there are no exceptions in mathematics, right? It's not a law; it's mathematics. So no exceptions. Or special treatments, saying that you are, right? Another example of this is if you have the open circle and then it's dislocated point, right? Is this function continuous? No, right? Can you differentiate the function? Yes. But again, the derivative does not exist at that point, at this point here, call that C. Derivative does not exist. Now, this is a relative min. It's still a relative min. You can see that, right? Because in this neighborhood, it's the lowest point. Maybe this goes down. Maybe it goes like this, and I put the point over here to be absolute, man. Whatever, right? But you see the idea of what's happening. So that's a little bit tough case. The rest should be straightforward. So now, what do we do? Well, we just learned how to locate min and max, and believe it or not, we are done with 4.1. You need to learn the types of extreme points. So you have local and global min, local and global max. And then you need to know that they occur when the derivative is equal to 0, because when we have horizontal tangency, or when derivative does not exist. And we just do the mechanics, do the few problems, and we're done with that section. So let's go and take a look at a few examples. There is also something with a closed interval, but let's do first problems and then we'll do that. So say we want to examine f of x equals tangent x. That's too much. Let's go with the simple stuff first. Let's go with x squared minus 1. Let's do the first one, right there. So x squared minus 1. Our job is to locate critical points. Now, when I say critical point is a point in 2D, which means has x and a y value, right? It's a point that you can graph. If I say location of the critical point, then x coordinate is just fine, right? So let's go with this. First derivative is 2x. We set that equal to 0. Set equal to 0 because, and when I put number 1, you know. We also know that polynomials, nothing weird happens there, no asymptotes, there are no spikes or cusps or anything like that. So we don't have to worry. When we have polynomials, it's just the first rule and that's it, we're done. So we divide both sides by 2 and get x equals 0. So where's the critical point? Well, now we find f of 0. I take this x equals 0, plug it back in original equation, and I get 0 squared minus 1, I get negative 1. So critical point is at 0, negative 1. That's the critical point. And what do I do with critical point? Well, that critical point could be min, could be max, or, this is another thing that we have to worry about, it could be inflection point. And we have to deal with that. That's going to be next lecture, talking about inflection points and what those are. But it could be, and I'll show the example immediately of how you can, but you'll know the whole story today, so it's not a rush. Now we know what the graph looks like, right? It opens upward, going through negative 1, and this is how we know it's a min at this stage of the game. And that's the procedure. Can I make this hard? Absolutely no. Can I make it annoying? Oh, hell yes, right? I can put a derivative where you have to go and use the logarithmic differentiation and then spend another 17 hours computing the value, right? Because look, every time you are computing critical points, you have to solve some kind of an equation, right? Whatever derivative gives you, you have to solve that equation. And those equations could be really annoying at some cases. Or very simple, like the one we just had. So let's see another example. How about basic Sine X, right? So we have Sine X, and let's limit that on 0 to 2 pi, all right? So I'm going to restrict domain because we know that the domain for sine is infinite, and we know that we are going to get infinitely many bumps. So let's just restrict it as we are just learning this for the first time. So what is the procedure for my critical point? Well, take the derivative. What's the derivative of sine? Cosine x. We set that equal to 0. Again, we don't have to worry about spikes, cusps, vertical asymptotes. You know, sine x has none of those. So set it equal to 0. And we set this one equal to 0. And now we have to solve the equation cosine equals 0. Okay, when is the cosine equal to 0? Not at 2 pi. We're going here. Here's the cosine. This is where your 2 pi is. This is where your pi is. Where is the cosine equal to 0? Yes. There is the pi over 2. Because you see that the cosine graph is cutting through x-axis. So that's y equals 0. So that's the solution. And then it cuts over here at 3 pi over 2 as well. So we have two critical points, pi over 2 and 3 pi over 2. Now, if you plug those values back in a sine to compute their y values, sine of pi over 2 is equal to 1. And sine of 3 pi over 2 is equal to negative 1. So I have a critical point pi over 2, 1. And I have a critical point 3 pi over 2 and negative 1. What are these? What's the first one? Min or max? It's a max. And what's the second one? Min. Is that a guess? That's a 50-50 chance. When I toss in inflection points, it's going to be 33.333% chance to guess, right? So let's pull all of these guys together. Graph a sine. That's where the 2 pi is. This is where the pi is. So clearly this is pi over 2. This is 3 pi over 2. So now these are all immediately clear because you see them on the graph. There is a max value here, which is pi over 2 and 1. And there is a mean value here, which is 3 pi over 2 and negative 1. But there is also this common sense part where the y value here is equal to 1 and y value here is equal to negative 1. Right? Can you make y equals negative 1 to be a max if there is a 1 floating about? The answer is actually yes, but you would have to have more mins and maxes around. Look at this. If I have, we're going to play now connect the dots. I don't know if you played this game before, ever. Can I make this point to be a max? The answer is yes, but I have to put a frown through it. See the frown? Because in order for it to be a max, it has to have a frown because it has to be a max at least in its neighborhood. But now I have to connect the function into this point, so I have to bend back and go into that point. You see how I created an extra minimum that is not predicted by calculus? And you can't have that. So, for most part, right, the highest value of all values you get is a max, and the lowest value of all values on y, right, that you get is a minimum. Just because if you think about this for a second, right, you say, okay, this is a max, and if I want the other one to be the max, the only way to connect them is to, right, because you have to smooth it out. But then you say, I don't want to smooth it out. How about I just, go directly and connect like this? Well, this situation here is called the cusp, and that is the D and E, and that would also be predicted by the number 2 rule from the critical point definition. So there's no way to escape. There's no way to have it any other way other than what it must be, and that is maximum is 1, minimum is negative 1, and if you try to force them backwards, you are going to run into troubles where you can't connect things. So in order for this to be a min, I would have to have a smiley through it. And now if to connect these two, I have to bend back and I have to bend back again. You see that if I have the wrong assignment for them, I'm creating 2 more. First of all, this looks nothing like a sine graph. Let's start there. But, so we are going to have some really scary looking functions, right? That you have no clue what the graph is, what the graph looks like. But you will always have, that little common sense bit where, all right, I have one number that is positive, one number that is negative. So, the chances are. Now, I'm not saying that it's impossible because we do have functions. But again, I would need to have a vertical asymptote or something going on. See? If I put a vertical asymptote and then this one follows this way and this one follows this way, then these roles are switched. But again, this is not a sine function. Draw the sine function and look at it. And say, okay, there's the max, there's the min. Right, these are the locations. So that's the part where, you sit down, you study, and you try to make these connections because there's only one way all of this can go. And that one way, it has to fit in a theorem and definition and everything that we put together. So let's recap this problem one more time. It's the standard procedure for every single problem. You will take the derivative of the function. You will be wary of the does not exist part. but for the most problems you set equal to 0 because you are looking for horizontal tangency where slope is 0 to find min and max. Once you are solving this equation, could be exponential equation, logarithmic equation, trigonometric equation, or polynomial, like we had up there, 2x equals 0. So it could be any kind of equation that you learned so far in your previous education, particularly in algebra and pre-calc 1. This is pre-calc 2, but straight. Solve the equation. In this case, we have two values, right, where we have x-intercept. So those values give us y values, and these are the critical points. Point is x comma y. When you go to calculus 3, x comma y comma z, right? So the number of dimensions, dimension y and dimension x, two dimensions was the 2D point, x comma y. So these are the critical points. And then we went one step further, because we know what the graph looks like. We can easily label this one as a max, this one as a min, and also use the common sense part. That's positive 1, that's negative 1. The chances are the vultures are back. And they're fighting. Okay. I'm going to sit here because I can't see them and then I'm not distracted. They really look scary, right? Does anyone have vultures as pets? How people? No, I don't know. People have all kind of weird stuff as pets. You don't know anyone? Good. For instance, okay. I'm not going to question his decision. I'm going to question you now. Why are you friend? Like, what are you gonna go? What are you gonna do? You go there and skunk is like, okay, you're next.
They take the sun out.
Well, that's cruel.
Yeah, it is cruel.
That's like someone wants to have you as a boyfriend and they just cut off your arms just in case.
Better than other things.
So, well, in that case, you can't fight. I mean, that's the point. All right, let's take a look at another example. Ooh, you're gonna love this. This is one of the examples in a textbook. Here's a function, which is x is 2/3, and then 2 minus x, to find critical points. And they said, well, we'll deal with the. Yeah, we can deal with the interval now. Okay, they give you the interval. So this is in a textbook, right? You can actually open the book and read it if you haven't. So what do? We take the derivative, and then we set derivative equal to 0, and find x locations where you have 0 slope. Let's find the derivative. Oh, it's the product rule, right? So copy the first times derivative of the second, which is just -1. Derivative of 2 is 0. Derivative of negative x is -1. Plus, copy the second, 2 minus x, times derivative of the first, that will be 2/3, x to the -1/3. Yeah, let's fix this. Right, let's make it prettier. Remember how I told you got to factor and simplify as much as you can because chapter 4 is coming, right? Like for how many seasons winter is coming? Well, it's here, all right? So no more. That was it, right? We had few months of chapter 4 is coming. Chapter 4 is here. Let's deal with the threat. So f prime of x is equal to -x to the 2/3 plus 2/3 2 minus x divided by x to the 1/3. See x to the 1/3 in a denominator. So now what should I do? Well, find the common denominator, and when I find the common denominator, I can have one fraction You really do not want to set this equal to 0 at this point. I mean, good luck. Go ahead. I'll wait. No, I'm coming back next Saturday. So what I'm going to do is I'm going to do the common denominator thing, where this is obviously over 1, and I'm going to multiply top and bottom by 3x to the 1/3 to have common denominator everywhere. So that's your intermediate algebra, so deal with it, right? Your common denominator is 3x to the 1/3. In the numerator, you have -3, and now x to the 2/3 times x to the 1/3, right? 2/3 times x to the 1/3. What do we do with this? You add the exponents. So 2/3 plus 1/3 is what? 1, right? It's 3 over 3. So this just becomes -3x. Yay, right? On the second one, you have plus 4 minus 2x when you distribute 2 in a parenthesis. And now, for the final here, you have 4 minus 5x divided by 3x to the 1/3, and that's equal to 0. We like when you have a single fraction, right? That's what we like. Because when we have a single fraction, we can cross multiply and denominator dies instantly, because denominator multiplies in a 0. This over here looked terrifying. And if you are to put equal to 0 over here, good luck, right? But when you look at the last thing over here that we have, when you cross multiply, this is what you get. And if you can't solve this, well, back to elementary algebra. Right, back to 7th grade or 6th or whatever, right? Because that's what it is. Now you have 5x equals to 4, x equals 4/5. Hope I did that right. So we found the location for the critical point. And that critical point is between -1 and 2, as you can see, because it is it's 4/5, right? It's less than 1. And it's positive, so it's more than -1, more than 0. So that was the procedure. And again, it's the same like every previous problem we did. Take the derivative, set it equal to 0, right? Go through all the calculations and come up with 4/5 at the end. Good. What should I do with the -1 and 2 on the interval? So we need to discuss that as well. Oh, I almost forgot. There is a critical point also at 0, right? Because we have vertical asymptote there. But it's asymptote. It's not a point. So we don't have to worry about x equals 0. I'm trained to kind of ignore it because it's the asymptote I already know. But some of you might go in and say, well, wait, what happened with the not defined, right? That's a critical point as well, at least the location. And yeah, you're right. So there is a vertical asymptote at x equals 0. Because when x equals 0, the denominator is 0. Numerator is 4, so you get 4 over 0. So there's a vertical asymptote at x equals 0. But for x equals 0, having a vertical asymptote there, right, it's not a point. What else did I want? Oh, yes, let's talk about the endpoints. Endpoints of the closed interval. So We need to test -1, 2. We found 4/5, right? But let me just draw, when you have closed interval, right? You have your sine look like this, you have your cosine look like this. If you do not have closed interval, right? Restricted domain, whatever you want to call it, this wave would go forever. And this wave going forever means infinitely many max, infinitely many min values. But as soon as I chop it off, 1 min, 1 max. Over here, max, max, min. Look that these guys on top occur at the endpoints. You know what's a crazy nice thing about closed interval? You always have min and max. It's either at the endpoint or it's somewhere inside. You're guaranteed to have it, because if you do straight line like this, there's your min, there's your max. The infinite line like that has no min, has no max. But as soon as you restrict that line with finite, there you go, min and max. What else? You can have the situation like this. There is your absolute max and there is your relative max. Both of those are max values. But you can have this. There's your absolute max now as the end point. So what we want to do is we want to test the endpoints. Because for the sine, endpoints are relative min, relative max. Absolute ones are inside. But for cosine on the restricted domain, you have absolute max values at the endpoints and the minimum absolute min somewhere inside. Over here again at the endpoints. So it depends on the function. Depends on the function. So what I'm going to do now is I'm going to compute all of these values for our critical points. What do I have? I have x equals -1, x equals 4/5, x equals to 2. What are the y values? Well, plug everything in the original function. F of -1. Great. F of -1, that's -1 to the 2/3 times 1 minus 2 minus 1 or 1 minus 2? 2 minus 1. Well, 2 minus minus 1, so it's 2 plus 1, but 2 minus -1. There we go. So what are the tools? When you square -1, you get +1, and cube root of +1 is 1, times 3, because 2 plus 1 is 3, we get 3. Now do the same thing for 4/5. So we have 4/5 to the 2/3, 2 minus 4/5. Let's do the 2 first. 2 to the 2/3, it's bad as well. And then 2 minus 2, ooh, this one is 0. I don't even care how much 2 to the 2/3 is, because 2 minus 2 over there is 0. So 0 times whatever number you get on the left is going to be 0. Now, what is this thing with 4/5? When I square this, I get 16 over 25. And then I have a cube root of that. Times, and over here, 2 minus 4/5 is going to give me 1 and 1/5 is 1.2. You can use decimals over here. I mean, you have to use decimals because you have a cube root of these values that you can't cube root anyway. So let's compute that real quick. Where's my, there we go. 16 divided by 25 is 0.64 raised to open parenthesis 1 divided by 3. And we have 0.86. 0.86. Again, I don't know what the graph looks like, but I just found points -1, 3. I found the point 4/5 and 0.86, and I found the point 20. What's the lowest of all y values? What's the lowest of all? 0. So this one over here is ABS min. That's the lowest. And what's the highest of all y values? 3. So ABS max. Again, when you are on a closed domain, meaning restricted domain, meaning you have an interval and tell you the function lives between these 2 points, you will always have absolute min and absolute max in that. Well, there's one case, the straight line, horizontal line, right? Every single point is min and max at the same time, so just that case is fine. But the rest? Oh, I forgot to multiply by 1.2. Yeah, I only computed the cube root. That's cube root is 0.86. What is that times 1.2? 1.03. Good. Thank you. 1.03. Whew. It didn't change the outcome of the final outcome of the problem, but it did change things. So good. All right. That's 4.1. Find the derivative, set it equal to 0, solve it with whatever witchcraft you can, and calculate y values by plugging those critical numbers back in the original function. Yes?
How do you know if this shows the middle point or relative to the max?
I have no clue unless I look at the graph. We are going to develop techniques now in 4.2 called first derivative test and second derivative test, which will clearly tell us what each one of these points is without guessing. Right? So far we relied on our intuition. We relied on a pre-knowledge of what these graphs look like, and then we were able to say what these points are. But when you have a function like this, good luck. Because we don't know what the graph looks like, but at least in the calculation over here, we are guaranteed these 3 points. These 3 points are either min or max, right? So the highest of all y values must be the one that is sticking up the highest. And because the line is not going forever, the line stops there. Let's do one more quick example, actually, to make sure. So y equals e to the 6x. All right? What are you expecting here in terms of min and max? What are you expecting? Do you know what this function looks like from pre-calc? There's no min, no max. Right? But let's compute. Let's see. So what do we have? We have y prime, the derivative, is equal to 6e to the 6x. And then you set that equal to 0, divide both sides by 6, you get e to the 6x equal to 0. And if you learned anything in your pre-calc 1 class, you know that this has no solution. To solve equation, you have to make 2 lines intersect, and their intersection is the solution. Well, if I draw e to the x, and I draw y equals 0, these 2 lines never intersect. So there is no solution, which means no crit points, which further means no min max. And once you draw original function e to the 6x, you know that it doesn't have min and a max because it asymptotically, right, or to the left and to the right goes up to infinity. It doesn't create any of those bumps to have min or a max. Now, can I have min and max on it? Sure, just cut it on the interval, right? If I cut this on the interval in any way, right, let's say cut here and cut here, well, the function goes forever up, then as soon as I cut, those points at the end would become absolute min, absolute max, because those would be the lowest and the highest points of all. But we're not going to do that, right? We're just going to have it on the infinite domain as it's supposed to be. And since they never intersect, they don't have it. So that's that. That's the first section. We're going to go now with 4.2. Talk about first and second derivative tests.